All right, yeah, good evening, guys. Thanks for attending the Alluxio Meetup. Really happy to be here with you guys tonight. And this talk, as Amelia said, is going to cover the Alluxio 2.0 preview release, which is the latest release of Alluxio that launched just last week. It has lots of cool, awesome features that I'll be talking about in this presentation. So a bit about myself. I'm Kelvin. I'm the release manager for Alluxio 2.0, meaning I have to take care of like all the Jira tickets, making sure the release gets published, things like that. And I've been working with the project, which from the days it was still called Tachyon. And that was like many, many years ago, I think like 2012. And as Amelia mentioned, I work at Alluxio. We're based out of this building. If you guys are interested, we're also hiring. So before we dive into the details of Alluxio 2.0, I wanted to give you guys a quick refresher, or for those of you guys who aren't that familiar with what Alluxio actually is. So Alluxio is an open source distributed storage system. We sit in between compute frameworks like Spark or Hive or Presto and traditional storage systems like S3 or HDFS. And what we're commonly used for is actually to provide a data access layer for OLAP on Hadoop workloads. So you can think of stuff like Spark SQL or Presto running on top of Alluxio, backed by storage from HDFS or S3. And as a technology, we've been deployed at many large internet companies and technology companies, some of which include Huya, Two Sigma, and Tencent. And to give you guys a sense of like kind of the scale and reliability of the Alluxio system, the 1.x release has been deployed at scales of over 1,000 nodes at many different companies. OK, so that's enough about Alluxio. And this is kind of like the agenda for the meat of the presentation, which is first we're going to talk about what was the motivation behind having a 2.0 release. Why not just continue making 1.9, 1.10? And then we're going to talk about kind of the architectural innovations, what we actually did from a technical perspective to achieve some of these benefits and features. And then finally, I'm going to go over what the release roadmap looks like for the 2.0 release. Yeah, so really, what motivated us to decide to go for a 2.0 instead of 1.9 or something like that? So actually, when we were thinking about releasing Alluxio 1 and like the 1.x line, we had actually a pretty narrow and defined set of use cases we wanted to address with the technology. So by the time we were releasing 1.8, we kind of already felt that the areas we wanted to address were pretty much there. The improvements we were making were kind of incremental. We're introducing some features that were improving like the usability and like the user friendliness, and we're making some optimizations to improve performance, maybe by like 5, 15, 20%, things like that. But by no means does that mean that Alluxio was done. A lot of the users and kind of people who we've talked to, they've been saying, Alluxio has been really helpful for us, but we wish that it could do this, or we wish it could do that. And all of those things kind of started to fall outside of what we originally targeted for Alluxio 1. So these things that they brought up fell into 3 different kind of categories mainly. First was they wanted to run more workloads on Alluxio. For Alluxio 1, primarily workloads resided in the Hadoop ecosystem. So people were using the HDFS interface, like MapReduce uses the HDFS interface. But now with kind of the rise of machine learning workloads and AI workloads, a lot of people wanted to run things that actually interacted with a POSIX file system. And those did not work very well with Alluxio. Another direction people wanted to go was simply data management, basically being able to control how data moves between Alluxio and the underlying storage systems. And all of those things we were happy to do, but we realized that the architecture of Alluxio 1 wasn't well suited for that. So in order to address that, we couldn't really just push out a patch release and change the entire underlying infrastructure. And the last thing that we heard from users really was just they wanted to deploy Alluxio more. They wanted to scale out their clusters. I mentioned that we scaled to about 1,000 nodes, and people wanted 2 times or 3 times that scale, and they had far more clients than we were able to support. So I talked about earlier that the kind of the planned use cases that we had for Alluxio 1 were pretty much getting near the mature cycle where people were just using Alluxio out of the box and it was working. So what were those? First one was to be able to burst compute into the cloud with data being on-premise. What this means is generally people decide, oh, I need to do some analytics on my data, but they don't have enough compute resources to do that on-prem because there's a lot of other batch jobs running on-prem. So the data scientists will want to just spin up some cloud instances and do a bunch of processing. But that's actually really difficult without something like Alluxio because you need to ferry the data from your on-prem into the cloud. And Alluxio does a really good job about making this transparent to the application, making it look like as if the data was just like in another on-prem storage system. So the second use case that we were looking at was really being able to enable object storage for these data analytics workloads. So traditionally, you run things like Presto or Hive or Spark. All of these guys run on a file system, like a Hadoop file system. But what we've seen in the past years is people want to move from file systems to object stores, just because object stores are a more natural way for people to store the types of data that they're collecting in these data analytics workloads. So what Alluxio does is it provides a really nice kind of API as well as performance characteristic shielding layer between the application and the underlying object store, making it look like the object store is just as good as, say, a local HDFS file system. And of course, the last thing, and where we kind of started from, was the idea of accelerating OLAP on Hadoop. So just being able to run your Spark SQL queries faster because of the in-memory storage. So all of these things we're still taking a look at in Alluxio 2, and will undoubtedly continue to improve and support these use cases. But what are the new things we're looking at in Alluxio 2? The first, as I mentioned, are the machine learning and deep learning frameworks that really want to be running on object stores. What we've seen is people have been running simulations on their local machines, but as they realize that their training efficiencies and things like that can all be improved by having larger data sets, they realize, oh, I need to fetch data from outside of my local storage system because it just simply cannot fit on one machine anymore. And the second thing that people want to do is just be able to manage a data lifecycle through Alluxio. OK, yeah, so the first thing is about the machine learning and deep learning workloads. What's our motivation behind this? We actually found like the main reason why we want to move into this space, outside of the fact that a lot of the people we talk to using Alluxio said, oh, I want to use Alluxio for machine learning, is that we looked at the data sets being curated by Alluxio. So the data sets that were already being used by these OLAP on Hadoop systems. And we realized that the data sets are actually the same as the ones that these machine learning frameworks wanted to provide. So what that meant for us is it's kind of like a natural continuation of our kind of data access layer to be able to serve these new applications. That, of course, doesn't mean that there's no challenges. There's a pretty large challenge in the fact that we're moving from the Hadoop API to a POSIX API, as well as these workloads have different data access patterns, different file characteristics, and things like that. So the second area of data management, what people really wanted to do in terms of managing data came in 4 different types. One was to just be able to manage data within Alluxio, so how many replicas you have of this block. Another really popular feature in Alluxio 1.x was the idea of async persist, which means that a user could write data to Alluxio, and in the background, sometime later, it would be written back to the underlying storage. This made writes really fast because you could just write at memory speed. But unfortunately, in Alluxio 1, we didn't have the infrastructure to make this scalable and distributed. And in Alluxio 2, we aim to address that. So on the flip side of kind of this idea of persisting data is the idea of loading data. A lot of people who use Alluxio as a read cache have to run their own jobs actually to load data in Alluxio 1 so that the data is kind of preheated in Alluxio. Now with kind of a framework in order to facilitate distributed work within Alluxio, we can do that natively so that it's much more efficient and people don't have to go around supporting their own scripts. And the last category of operations is the idea of moving things between mount points. So Alluxio provides a unified namespace, meaning that you take a look at your namespace, it's all under one kind of root tree, but that could be backed by HDFS, it could be backed by S3, it could be backed by Azure. And when you try to move something between, let's say, Azure and S3, the system in Alluxio 1 is just going to say you can't do that because that's not, like, these two are not the same mount points. But in Alluxio 2, we decided that that's actually a logical operation that a lot of people want to do. So we've developed the infrastructure so that you are able to do that seamlessly without having to write your own jobs to transfer the data. Okay. And the last category of things is around scaling. And when we took a look at scaling, we tried to scale in 3 different directions. The first being namespace scaling. So the number of files that Alluxio could support hovered between like 100 to 400 million files. And this wasn't really sufficient for people who wanted to use the unified namespace feature, because they would have multiple HDFS clusters with like 200 million files each, or like 600 million files. And once you brought them all into Alluxio, the master would just not be able to support that, because we had a very similar architecture to HDFS. So we hit similar kind of scaling boundaries for the namespace. But in Alluxio 2, we revisited that, and we are able to scale on the order of billions of files. Another kind of dimension of scaling is the idea of cluster scaling, like how many nodes can you have in the cluster. And here we aim to scale to about 3,000 nodes. And hand in hand is how many concurrent clients can you have talking to your Alluxio system. And here we aim to get up to about 30,000 concurrent clients. You can think of these as, if you're running a Spark task, basically how many Spark tasks can you have running at the same time. Okay, so I talked a lot about kind of high-level goals and like different benefits and features, but how did we actually achieve any of this stuff? So these are the kind of technical innovations that we made in Alluxio 2.0, and all of these are available in the 2.0 preview release. So if you're interested in checking that out, or if any of these features are exciting to you, you guys can download that from our website. The first is off-heap metadata storage. This is how we enabled the namespace scaling of up to 1 billion files. The second was switching to our gRPC-based transport layer. This is how we scaled the number of nodes as well as the number of concurrent clients. The third is to improve the POSIX API. This would allow us to support the machine learning workloads which really prefer to use a POSIX file system API. The fourth is the introduction of a job service, which is actually a set of processes that run alongside the Alluxio workers and masters. This served as a lightweight computation framework that enables us to do a lot of the data management that we previously did not have a good way of doing. And finally, we've introduced an embedded journal and internal leader election framework so that we no longer need to have external dependencies in order to run certain workloads with object stores. Okay, so I'm going to go into a bit more depth for each of these features to give you guys an idea of like what the underlying implementation is. The first, for off-heap metadata storage, what we did here is we used a RocksDB embedded instance, and we used that to store the inode tree. So this stores the inode tree on disk, meaning before we had all of the inodes would be stored in the Alluxio master memory, and that would kind of scale with the amount of memory you would be able to allocate to your Alluxio master. The problem with this is once you scale past like 500 gigabytes of memory on your master, you would run into serious GC problems where your master would be unresponsive for like periods of time. So what we decided to do is to move the metadata to off heap, so kind of disk storage. But obviously the problem with this is disk is much slower than memory. So when you come in to access the data, it's going to take a lot more time to get it from disk than from memory. So to circumvent this problem, we built a in-memory cache for the frequently used inodes. And what we found here was it's actually pretty much the same performance for a lot of the workloads we ran, because most people, out of their like let's say 1 billion files, they're only using like 100 million or like even less than 100 million at a time. And as long as the working set is able to fit within the internal cache, the performance is pretty much exactly the same as the previous on-heap performance. The second set of kind of infrastructure changes we made was to switch to a gRPC transport layer. In Alluxio 1.x, we had 2 different types of transport. One was Thrift for metadata, and another was Netty for data. In Alluxio 2, we consolidated these two and used just gRPC for data transport. This, of course, like helps us write the code a lot better, but it also has a few critical features that enabled us to scale the cluster sizes. The first was the idea of connection multiplexing. So previously in the Thrift world, every thread that needed to talk to the master had its own connection. So if your Spark executor, let's say, is running 32 tasks, that's going to be 32 connections to the master. Whereas now, when you're able to multiplex, each application only has one connection to the master, and kind of all of the threads share that connection. So that's what multiplexing means. And the other feature that we leverage from gRPC is the threading model that is provided by gRPC. Previously, when a request came into the master would have to spawn a dedicated thread to serve that request and finally return that response. So that meant if you had, let's say, 20,000 concurrent clients, that's 20,000 threads on your master that need to be running at the same time. And that run into all kinds of problems around like file descriptors, around the heap and stack space. With gRPC, they provide a way to use a fixed size thread pool to serve all the requests. OK, so let's talk about the improved POSIX API. We previously provided POSIX support through Alluxio Fuse, and we continue to do that. But what we did in this release, different from previous releases, is we found out that the POSIX interface is actually really nuanced, and there's a lot of subtle things here and there that applications rely on. For example, if I call like open, and then afterwards I call like set attribute, that has a specific interaction compared to calling just set attribute before. So what we did is we decided we're going to focus primarily on the TensorFlow workload, because that's one of the hottest machine learning apps that people want to run on top of Alluxio. And we ran through quite a few different TensorFlow algorithms, like image recognition and recommendations. And we kind of made sure that for each of these workflows, the Alluxio POSIX interface was providing the correct file system semantics that TensorFlow was looking for. And this is kind of an area where I actually think the community has been helping us a lot, in the case that they can identify which POSIX-based workloads they're interested in running on Alluxio, and we can then incorporate those into the Alluxio POSIX interface. So the next thing I want to talk about is the job service. So this is actually another set of processes that run alongside the Alluxio processes. And this really allows us to spawn different tasks that do very heavy operations, like moving data from one storage system to another, without having it burden our serving servers, which are like our masters and our workers. So some examples of what you could do with the job service: you can control how many replicas are in Alluxio, because the job service can, in the background, load data in when the replicas are too low, or evict data when the replicas are too high. We can also persist and load in a distributed manner, because we have a bunch of processes that are able to do distributed computing for us. And also, we're able to do data transfer between mounts, because we can just send this task off to the job service, and it'll happen asynchronously without the user's control. So the last thing I want to talk about is the idea of the embedded journal and the internal leader election. So there's been quite a bit of issues running Alluxio with object stores, because we rely on an external distributed system in order to store our journal. So without that, you can't really run Alluxio in fault-tolerant mode. And journals are very difficult to store on object stores. So to get around that issue, we actually implemented our own raft quorum between our Alluxio masters, so that they can internally do journaling with just their local storage systems. And one of the benefits of that is it also lets us have a quorum to decide other things which we may need consensus on, including leader election. So previously, we used Zookeeper in order to decide, hey, which Alluxio master of your many masters is the leader. But now we actually don't need a Zookeeper or any external distributed storage to run Alluxio in fault-tolerant mode. OK, so that's it for the features. Now I wanted to give a short overview of what the release roadmap looks like. So right now, today, you guys can go on our website and download the 2.0 preview release. This release is really intended towards kind of the bleeding edge users, as well as developers who want to try out these new features. And we really appreciate any feedback or comments you guys have. We've also moved from Jira to GitHub issues, so hopefully that will be an easier portal for anyone to raise issues or bring up suggestions. And in terms of the actual 2.0 official release, we plan to do that sometime this summer, so in about 3 months. Okay, yeah, so that's it. I think there's quite a few resources up here if you guys are interested. We now have a Slack channel, so you guys can chat with us in real time if you have questions. And we host lots of office hours and webinars regularly if you're interested in hearing more from the Alluxio community. All right, thanks guys. If you guys have any questions, I'm happy to take them now, or I'll hand it off to Wanchun.